Okay. All right. I'll wait for FF play to show up. Let me. Whoops. Okay. And change Tmux window. All right. So today I will be covering how to do the abstract, how to build up the abstract syntax tree, arenas, and operator precedence. All of these are actually pretty easy, and I don't know why they seem to overcomplicate it. Okay, so the way I do it is I build up my abstract syntax tree based on the order of operations. So let's say we have A times B plus D times C. And I actually explained this to my mom, and she got it, and she's not even like a programmer or computer science person. So, so yeah. Okay. So this is how we're going to want our abstract syntax tree to look like. If you don't know how an abstract syntax tree is evaluated, I'll go to the eval function. So evaluate AST. Okay, over here. So it's it recursively calls itself. So it does. So for this, it'll do plus the left node, and then the evaluation of the left node, and this plus the evaluation of the right node, and then this will be the evaluation again of the right node, and this one actually returns a double. This is actually multiplied the double here, multiplies this double, and it goes through the entire thing. You can look at it here. This is for the addition. This is for the multiplication. Actually, let me increase. And this is for when the number shows up. All right. So let's go back to the main. All right. So how do we get our tree to look like this? Now the way I did it is again, operator based on the what's it called, order of operations. So let's number our array. So 1, 2, 3, 4, 5, 6. Okay, and we know that the order of operations based on PEMDAS will be this multiplication first, the one at 1, then the one at 5, and then the one at 3. I almost wrote a plus. All right. I'm going to delete this and then we'll build it up later. Okay. So first we're going to want to show like that we can sort this efficiently. So I'm not using quick sort, I'm not using bubble sort, I'm not using insertion sort, any of those sorts. I'm using like a radix sort, okay? So here's how it works. We have an array. Obviously, we're going to have more operations, but let's say we have a multiplication array and an addition array, all right? And then when we move our pointer over here, our lexer, we go to 0, all right? That's a number, we don't care. But that's added to our evaluation token array. Then we go to 1, all right? We check what this is, all right, and we do this at the time where we evaluate the token, all right, and then we add it to our multiplication array over here as 1. Okay, and I think you can already see where this is going. We go again until we reach our addition. All right, we see that this is addition and that it's at 3. We put it here at the end, and then we keep going. We see that we have a multiplication at 5, and now we just concatenate these arrays and we get 1, 5, 3. Okay. Now let's go from this order of operations, from this index array of operations. So I call it operations index. I don't remember where I set it up. Yeah, right here. Maybe all of this should be allocated together, but I'm not going to bother doing that. All right, so our operator index is like this. I'm just going to call it ops idx here. It doesn't really matter, okay? So now when we build up our abstract syntax tree, oh yeah, this is where we sort it, and this is where we build our abstract syntax tree. We start from the bottom up, actually. We look at 1, we say, this is our root node, and we do a multiplication, right? And then we look at the left is A. We look at the right node, it's B. Okay, we're done with this. Now, let's look at 5, okay? We set this up as another tree, multiplication. We look at the left node, that's D. We look at what's at the right in the index in the array, and that's C, right? And finally we do addition, okay? Plus, that's at 3. We look at the left, that's B. Okay, this is wrong. We want a tree. So we keep track of the parents in each node, at each node, okay? So when we detect that a node has a parent, we make it so that when we are looking at this, we sort of shift our node over here, up here, right? And then we do the same here. And if you recall, this is the exact same abstract syntax tree as we did before, okay? But there's a problem. What if we want to do a subtraction at the end over here? So minus E. All right. So the way we're going to do this is our new thing here is going to be at 7. Okay. When we look at the left, we'll see that it's at C, and at the right, it's going to be E. Okay. So now, okay, C has a parent. We climb up here, and it points to this one. This multiplication also has a parent, and then we point to the addition. And finally, we do the addition. Problem is, and we check if the addition has a parent. It doesn't, so we know that we enter here. Problem is, why did we check? We're going to be checking more and more depending on how our tree looks. So instead of just keeping track of the parents, I wrote this at 2 a.m. So it could be like very a little, we could add some things that we don't actually need. But on top of keeping track of our parents, we keep track of a root node. All right, so let's move this entire tree and let's put it right here. All right, and now every node, so we've generated an array, a root array. And this is the length of the amount of ops. All right, or operations. All right, and and then we have every single node has a root index field. Okay, and what's inside here is the index of an operation. So okay, now every node has a root index field. When we generate a tree, so the multiplication. Let's look over here. When we generate a tree, we have a root array, and at 0, all right, we generate this multiplication sign, or the multiplication node. It has the root index 0, and it points, so it has the 0 array here, and that is set to the multiplication index. So we start at 1. Okay, right, and this one is 0. For A, we did the same here. So the left side, the root index is also 0. So this one is 0, this one looks at 0, and right now 0 is 1. Okay. We do the same. We do something similar for D. This one is at 1. This one is at 1. This one is at 1. And this points to where this is. So this points to 5. Okay. Now when we do the addition, when we look at B, right, we update the root. Okay, so we look at B, we say okay, point to this root and check if the root has a parent. Okay, so it points, well actually It goes to the parent and checks if the parent has a root. This actually doesn't make any difference, so I don't know why I did it like that. Again, I set it to I did this at 2 a.m. so it's kind of weird. So yeah, we go to the root and check if this root has a parent. It doesn't. All right, and so now we set that the one at 0 is equal to this new one at 2. All right, so 2, and this one is 3. All right, and when we do this, we update this to 3. All right, and now this whole thing, all of these 3 have immediately been updated to point at this top plus node. Okay. We do the same for the D. So when we look at D, all right, we go to the root node, check if this one has a parent. It doesn't, and then we set that the new root is the plus at 5. At 3. And now, when we go to this minus sign, we look at the root node of this parent. It's at 3. Okay. We set up a new one. This one should be 3, and this one at 7. 37. All right. We look at this minus sign, and then we update what's at C. So we update this whole thing here, this parent. And we point to this root node. Actually, I did it kind of inefficient. I did it inefficiently, I think. Yeah. Because this one will only update this this 2. So the new one here is at 7. Yeah, so this points to 7. So when we go to this root over here, we go to 7. Now this isn't exactly a problem because once once it's surrounded, once a node or once a number is surrounded with operators, it can't really be accessed again. So it doesn't really matter. Yeah. Now, you may be wondering, how do we do right associative operations, and how do we do parentheses? So let's cover right associative operations. Let's do some exponents over here. All right. And if you can verify yourself, but the new order of operations will be 7, 5, 1, and 3. Okay. And we do the same iterative algorithm. So let's set up our exponent, our multiplication, and our addition arrays. We see that 1, we check first. We have this 1 over here. Then we have a 3 over here. And then we have a 5. And then a 7. And the way we do right associativity is at the moment of array concatenation. So when we look at the exponent 1, we actually start at the end. So we go 7, then 5, and then 1, and then 3. And building up the abstract syntax tree is left as an exercise for the reader, or the viewer, I guess. And finally, how do we do parentheses? So let's look at parentheses over here. Now the trick is we also add another bucket. Okay. Oh, and you can see over here when we're concatenating the array, this is where the right associative exponent index goes. Same goes for the negative one. That's also right associative. All right. So this is how we do it. So we look at the length and then we shove it at the end. All right. Now, let's look at the order of operations here. Clearly, we have a parentheses here, so that's a 3 first, and then our 7, 5, 1. The trick is we add a new bucket. We actually have an array of parentheses, and we do our nesting level. So here, our nesting level 1, and then we have an exponent array, a multiplication array, and then an addition array. But right now, we're just going to worry about addition because that's the only thing we have. All right, so we go through it, and we assign first, so the parentheses level 0, and then we go to the exponent, we do parentheses level 0, and then we do the multiplication. All right, and now let's just iterate through this. 0, 1 goes to the multiplication first. All right, 2, 3. The nesting right now, we're keeping track of the nesting as well. So originally we're at 0 nesting. We see this parentheses, and we know that the nesting level is now 1. So we increment the nesting level to 1, and then we see that this is an addition. We're at the parentheses level 1, so we put this at 3. All right, we keep going. When we see this left parentheses, we decrement the nesting level by 1. All right, and we see we have a 5 over here, and then a 7. And now we do the same concatenation. 3, 7, 5, 1. And you can write the abstract syntax tree with the method we discussed before. All right, so that covers generating the abstract syntax tree. This is pretty easy. I didn't really need to do prep parsing. I didn't actually get when I looked at 2 prep parsing videos, and I didn't really get them or why they'd be useful.